projects. In this video, we are going to explain about a project titled Software Defect Estimation using Machine Learning Algorithms. So now coming to the introduction part, the integration of machine learning algorithms into software defect estimation represents a promising advancement in the field of software engineering. By harnessing the power of data-driven predictions, developers and quality assurance teams can make more informed decisions about resource allocation, risk mitigation, and overall software quality improvement. As this approach continues to mature, it holds the potential to revolutionize how software defects are managed and prevented, ultimately leading to more robust and dependable software applications. One of the key advantages of using machine learning for defect estimation is its ability to adapt and learn from new data over time. As software development evolves and new features are added, machine learning models can be trained on updated datasets to improve their predictive capabilities. So now coming to the objective part for this project, the software defect estimation using machine learning algorithms revolves around optimizing defect prediction accuracy, enabling early defect detection, enhancing resource allocation, fostering continual learning, and ultimately elevating software quality. This approach harnesses the potential of machine learning to transform how defects are addressed within software development, yielding tangible benefits in terms of efficiency, reliability, and customer satisfaction. Resource allocation optimization is another important goal. By predicting areas of the code base that are more likely to contain defects, machine learning-based defect estimation aids in the efficient allocation of development and testing resources. So now coming to the requirements part, we have two types of requirements, that are hardware requirements and software requirements. In hardware requirement, operating system as Windows is required, processor i5 and above, minimum 4 GB of RAM is required, hard disk 20 GB and above. Coming to the software requirement part, Python IDEL, that is 3.7 version is required. So now coming to the methodology part, first upload NASA software dataset. The first step is to upload the NASA software dataset, which contains relevant data about various software projects, including attributes related to code complexity, developer experience, project size, and defect occurrence. Second, run multi-layer perceptron algorithm. The multi-layer perceptron, that is MLP algorithm, is a type of neural network that can be employed for software defect estimation. By feeding the dataset into the MLP model, the algorithms learn to identify complex patterns in data and predict likelihood of defects in different parts of the software. Third, run radial basis function algorithm. The radial basis function, that is RBF algorithm, is a machine learning approach that utilizes a Gaussian function to model the relationship between input data and target outcomes. By training the RBF model on the NASA software dataset, the algorithm learns to map input features to the likelihood of defects. Fourth, run support vector machine algorithm. The support vector machine, that is SVM algorithm, is a powerful technique for classification tasks, making it suitable for software defect estimation. By selecting appropriate features from the dataset, SVM aims to find a hyperplane that optimally separates data points belonging to different classes. Fifth, run bagging algorithm. Bagging, short for bootstrap aggregating, is an ensemble learning technique that combines multiple models to improve predictive accuracy. By training several models on subsets of the data set and then aggregating their predictions, bagging reduces the risk of overfitting and enhances generalization. Sixth, run random forest algorithm. The random forest algorithm is another ensemble approach that builds a collection of decision trees. Each tree is trained on a different subset of the data and their predictions are combined to make a final prediction. Seventh, run naive Bayes algorithm. The naive Bayes algorithm is a probabilistic method that leverages Bayes' theorem to make prediction. It assumes that features are conditionally independent given the class label, which simplifies calculation. Naive Bayes is particularly effective when dealing with high-dimensional data. It can be applied to software defect estimation by modeling the probability of defects based on feature values. 8th, run multinomial NV algorithm. So here, multinomial naive Bayes is a variation of the naive Bayes algorithm that's specifically designed for datasets with multiple classes and discrete features. This algorithm can be useful for software defect estimation when dealing with categorical or count-based attributes. 9th, all algorithms accuracy graph. After running each algorithm on the NASA software dataset, the next step is to evaluate their performance. By comparing the predicted results with the actual defect occurrences in the dataset, accuracy scores for each algorithm can be calculated. These accuracy scores can then be visualized using a graph, which provides a clear comparison of how well each algorithm performed in terms of defect prediction. So now coming to the execution part, to execute the project, first we need to open the code folder. So here we have a folder named as dataset. In this we are containing some dataset over here in the .txt file. Another folder named as icons. In this we are containing some icons over here. And here this is the Python file which is containing the Python script in it. And here this is the run.bat file. Instead of executing the program in command line interface, we created Windows bat file to execute the project. Now to run the project, double click on run.bat file to execute the project. So here this is the graphical user interface. With this we are interacting with the program. Now click on upload NASA software dataset button to upload the dataset. So here I am selecting this cm1.txt file over here, and now click on open button to load the dataset. So here on this screen you can see that the data length is 498 and the training length is showing 398 and splitted tested length is 100. So now click on run multi-layer perceptron algorithm button. So now after clicking on the run multi-layer perceptron algorithm button for generating the model for calculating its accuracy. So here on this screen we can see multi-layer perceptron FM score, F measure, recall, accuracy values, and scrolling down the text area you can see all the details over here. So now here we can see multi-layer perceptron accuracy is 93%. Similarly, you can click on all algorithms button to see the accuracy and click on all algorithms button for calculate the graph. So here now I am clicking on run radial basis function algorithm button to see its accuracy. So here you can see the radial basis function accuracy is 50%, and now we have to click on run support vector machine algorithm button to see the accuracy. So by scrolling down the screen, here is the 94% accuracy, and now click on run bagging algorithm button for its accuracy. Here it is showing 94%. Now click on run random forest algorithm button. So again you can see the accuracy here as 93%. And now click on run naive Bayes algorithm. So here you can see 82% accuracy, and for run multinomial NB algorithm you can see the accuracy as 56.99%. For all algorithms accuracy graph, for seeing the graph you have to click on this button, and here you can see that x-axis represents algorithm names and here y-axis represents accuracy of those algorithms. In all algorithms we can see MLP bagging is giving better accuracy over here. So now closing this graph. So now coming back to the conclusion part, as the field of machine learning continues to evolve, so too will its impact on software defect estimation. With ongoing research and innovation, the potential for further refining algorithms, addressing challenges, and improving predictive accuracy is considerable. Embracing this technology-driven approach to defect estimation has the potential to reshape the landscape of software development, setting a new standard for quality, efficiency, and reliability in the industry. This leads to efficient resource utilization, ensuring that critical parts of the software are thoroughly scrutinized and fostering a more proactive and targeted approach to defect mitigation. The machine learning driven approach to defect estimation also promotes continuous learning and improvement. As new data is accumulated over time, these algorithms can evolve and adapt, capturing emerging trends and patterns in software defects. This adaptability enhances their predictive capabilities and ensures their relevancy as software systems develop and change.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.